Okay, great. So this you might have to do second time more because it is only giving us 40 minutes thing. So, okay, if my audio and video both are visible, I will share the screen again. So if you won't be able to see the screen, just let me know. Is it visible? Hello?
Yes, ma'am.
Okay,
Yeah.
great. So now we can just, so we were what actually doing? I was actually talking about this molybdenum in this particular, we have to find out the oxidation state of the molybdenum when it has been connected to the cycloheptatrienal ring. So here, if you realize, it is coordinating with the whole ring, and here it is giving no charge. So this particular cyclo ring, that cyclohepta ring, it is having no charge. So when you have to calculate the oxidation state of your metal, you need to find out whether it is having any charge or not. So since it is having no charge, so this will give you an oxidation state of 0. So molybdenum is your 0 state. Also, you can back calculate. It should form an 18 electron complex. So if your molybdenum, it is how much electron? It will give you 6 electrons. And for 18 electron complex, your this particular thing has to be 6 electrons. This also has to be 6 electrons. In total, it will give you 18 electrons. And in that particular 18 electron case, your molybdenum has to be in 0 state. That's why your cycloheptatrienal is neither having a positive or a negative charge. And it is basically, it is now having a 6 electron load, 4n plus 2 pi electron load. So it will not going to take any charge from outside, or it will give charge to the metal. That's why molybdenum is actually acting as a 0 oxidation state. So you can calculate it both ways, neutral as well as ionic. Since the ligand and your metal is having 0 oxidation state, both will be giving you the chain total valence electron count. Is that okay?
Yes, ma'am.
Okay. So So we will move to this next question where it is asking that C8H8 ligand is called what? What is this ligand called? So is it cyclobutadiene? So how we can eliminate these options? Firstly, this is C8. So it can't be buta, neither it can be hexa. So these options got cancelled. Now the only option left is cycloocta and cycloocta over here, C and D, diene or tetraene. So this is actually this particular shape here to have that C8H8. This is one edge, this is second edge, third edge, fourth, 5, 6, 7, and 8. So how many enes are there? 1, 2, 3, and 4. So this is cyclooctatetraene. So this is another question that has been solved now. Now the other question is you have to identify that here. What is this orbital representation of? Like this orbital representation belongs to which one of these? Can you answer, Chandan?
No, ma'am.
Okay, I'll just help you out with this. So here when we see, we have p orbitals, we have d orbitals. S is simply having this spherical shape, so we don't have to worry about it. I will just quickly explain what could be the possible geometry for all the orbitals, S, P, D, and F. Okay, so here we will see the orbitals with some different color. Now, if I talk about the s orbital, it is spherical in shape. Okay, so this is actually not looking like a spherical. You can just assume it to be a spherical. So p orbital, is having three main px and py. If you define any axis, so z, x, and y, so your x should be lying in this particular direction. So this becomes positive and negative lobe, px. If I have to have pz, so it should be along the z direction, pz, and y should be somewhat tilted. It should be like this. Is that fine?
Yes, ma'am.
Now,
Ma'am.
if we see d orbitals are further classified in five. So it is dxy, dyz, dzx, dx square minus y square, and dz square. So if I'll define the axis. So firstly, since it is involving the two axes, I am giving it as an x and it is x and y. So these d, x, y, y, z, and zx, they involve in the or along the axis. So in between the axis, so we have to make like this. So this is your dxy. Similarly, for yz, if I have y over here, if I make z over here and y here, also again, the loads will be in between the axis. And similarly, if I'm changing the axis from x to z, so again, it would be having in between the axis. So these are dxy, dyz, dzx, which will come under T2G orbitals that you will read later or you might have read. Now coming to these dxy squared and dz squared, these which comes along with your axis. So dxy squared, it's along the axis where it is x and it is y. And dz squared, it is actually looking like this where negative lobe is here. So this is along the z-axis. So this was the question. These are the different orbital shapes that we look into consideration and how the combination has been formed. So I've told you about the s orbital, p orbital, and d orbital. So the question says, they have given you this picture and they have asked, what is this shape? What is this orbital? So this is nothing but your dz square. Now it is understood.
Yes, ma'am.
So similarly, we have F orbitals, which are 7 in number. So that also you can cross check. And if you find any problem, you can let me know in another class. Now we'll quickly see some other question if we have left in week 0 assignment. Okay, this is done. Oh, this is done. Almost some questions are left. Okay, this question. So this question asks the energetically lowest filled orbital in the ground state molecular orbital of butadiene ligand is given by. So you need to check whether which one is the lowest one, and you have these cyclobutadiene bonds which you have to make, and this is Psi1. The other one would be having both are doubly occupied, and the answer to this question is Psi2, which is the lowest, energetically lowest field in the ground state of your butadiene. Similarly, you can find out ki this is HOMO, this is LUMO, and this way you can assign your, with respect to the energy, you can assign your molecular orbitals. So this was all about your week 0 assignment. I hope this has cleared your doubts. You just go through and see and try to attempt those questions again. And if you have any doubt on these questions, you can let me know now itself so that before moving to week 1 assignment, we should be able to clarify these. So should we move to week 1 assignment?
Yes, ma'am.
Okay.
Yes, ma'am.
So can you see my assignment 1, week 1 assignment?
Yes, ma'am.
Okay. So the similar way that we have said ki how it is going to work, whatever the basics that we have gone through till now. So the first question in the assignment that you have to attempt, I can't tell you the answers. Already we have discussed all the basic concepts over here. So week 0 was to make sure that you and all of us are on the same line. We understand the basic things. Now this week 1 assignment you have to solve because the deadline is tomorrow. The first question is the metal to ligand interaction in a transition metal allyl complex comprises of. So you need to understand before answering the question, you need to know that they are talking about metal to ligand interaction. So both are different concepts. If they are asking ligand to metal, that becomes different. Okay, so what they are asking for the metal to ligand interaction in a transition metal allyl. This metal and allyl complex, they're asking for the metal to ligand. So which also they have given that Psi1 and Psi2 are the molecular orbitals which are occupied and Psi3 is unoccupied. This is W occupied, that means your C3H5 would be minus charge. So it would be having 4 electrons as I was telling. So see, Psi3 is unoccupied, that is, it is antibonding. Now you need to know that metal is interacting with your ligand. The metal is charging, giving electrons to your ligand. So what could be the possible answers of that? So for that matter, we need to see. So for that matter, we need to know what is Psi1, what is Psi2, and what is Psi3. Psi1 is nothing but your bonding orbital, which which we talked about earlier also, with no nodes. So this is your bonding molecular orbital. Psi2 is your non-bonding, having one node. And Psi3 is your anti-bonding. So this is positive, and this is positive. One node here, other node here. So this is anti-bond. Okay. So when Psi1 gives electron to metal, that will form a sigma interaction. But this is a ligand to metal interaction. When Psi2 goes to bonds with metal or interacts with metal, that is a pi bonding, which is again a ligand to metal interaction. And the third one is Psi3 metal, but here metal interacts with your Psi3. So what kind of binding it would be and what do we call it, that you have to answer in this particular. Now you need to answer in your assignment. I have already cut down your 4 options to the 2 options because it is in asking that metal to ligand interaction we are talking about. So Psi1 to M, it is ligand to metal interaction, which is sigma bonding. Psi2 to metal, it is a pi interaction, which is again a ligand to metal because ligand is giving electrons to your metal. The metal is having empty orbitals or something like that. So there they are sharing or making a sigma or pi bond, but that interaction is going from your ligand to metal. That's why the arrows here defining as Psi1. Psi1 is of ligand to metal. Psi2 is of ligand to metal. Now the 3 and the 4th option, it is having a reverse sign where metal is showing arrow towards Psi3 and metal towards Psi3, where Psi3 is anti-bonding of your ligand. Now, it could be either pi interaction or your sigma interaction, depending upon the nature of your Psi3. So that you have to answer by yourself by going through the lectures. So this was the approach for this particular question, that we need to know what kind of interaction they are talking about. Is it metal to ligand or ligand to metal? But if it is metal to ligand, the first 2 options themselves get eliminated, and then we only have the CMD option. Is that clear?
Yes, ma'am.
Okay. So moving ahead, I would be explaining the answers in next week live session. But since the deadline is tomorrow, 8th February, so you just go through that once and try to attempt this assignment. You can attempt it again. So that would be enough. Now the second question says, this is the complex that has been given, nickel, which is having a C3R3 kind of system. So in the same lecture series, we have C3R3 cyclopropynyl cation. It is called as cyclopropynyl cation. This is also acts as a ligand, where it is binding with the nickel, and other ligands are pyridine and bromide. Now, if you calculate, now it is saying that if it interacts with this thallium cyclopentadienyl system, where thallium is your metal and Cp is acting as a minus, under the conditions of CC6, which is nothing but your solvent at room temperature. So what would be the reaction which is possible over here? So the best approach to solve this question for these kind of reactions, already this reaction is being covered in your lecture, so you can go cross-check that also. But here, what approach you can just see, you just calculate the number of electrons, valence electrons here. So pyridine will give you 2 electrons. It's a neutral system. The structure of pyridine is this, where the 2 electrons are there. It's a neutral moiety. So it will give 2 electron. Similarly, this 2 electron, bromide will give you 1 electron. It's Br minus, so 1 electron. This whole species, the cyclopropynyl species will give you 3 electrons, and nickel would be having 10 electrons. Now, if we calculate 2 plus 2 plus 1, that is 5. 5 plus 3, it's 8, and 8 plus 10, it's 18 electrons. So since we are not changing, if there is no oxidative or reductive, so there is no change in total electron count. So if you'll calculate the total 18 electron count in your product, so out of these 4 options, if you calculate which one is giving you 18 electron, the answer is very straightforward. And also it makes sense that Cp is going, this is a negatively charged, it has to replace some of the negatively species, and also some other solvent molecules will go out. So that was an approach to see that 18 electron reactant or the substrate will go to form an 18 electron product itself. So you can cross calculate all the total valence electron in this also. For example, if I'll take this particular example, pyridine is 2 electron, this is 2, this is 1, and Cp is 5, and this is 10. Now 2 plus 2 plus 1, that is 5, 5 plus 5 is 10, and 10 plus 10 is 20. So this can't be the option because it is making a 20 electron, right? So also here the charge of the nickel is +1. It is in +1 state because of the 1 bromide. Now when bromide is being replaced by the Cp, that should be giving, here it is nickel +2. Down it is here in nickel +2 state. So that's why you have to calculate your number of electrons, total valence electron count in both your substrate complex and your product complex. That will give you one single approach to look at this. Other way is to see into the insights of this, particularly when cyclopentadiene with 5 electrons is coming into picture. So if it is coming with the 5 electrons, what could be the possibility to replace the other 5 which is already present over there? So that you have to understand and to calculate the number of electrons and to get the product answer. Is that clear, or I need to repeat it?
It's clear, ma'am.
Okay, great. Now we are moving to the third question. Third question is also, I guess if you're smart enough, you'll be able to know how the second and third questions are related to each other. So the third question also, it's the complex already being given. When this complex gets crystallized out and we get to calculate the bond distances between the nickel and carbon. So this has been covered in the lecture series also, where the nickel carbon distance you have to predict, and these are the options. 45 picometer, this can't be the possible thing because it is having a metal carbon, so it is having a certain range. So you need to find out which one is the suitable distance for the metal carbon of the C3PH3, not just the metal carbon. They could also ask you for the nickel carbon of cyclopentadiene, but they are asking for the C3PH3. So you need to consider this C3PH3, which is having a total charge of positive. Okay, so now this question also is straightforward, which you can do. Now the again question is coming on the same complex, the three equations on one single complex. So it is easy to imagine if you have understood the second question itself. So in the fourth question, it has been asked that the total valence electron count of the metal center in the CpNi, which is nickel, C3APH3 complex shown below is. So you need to calculate the total valence electron count, which we have already done. How much electrons Cp does give? Can you please answer?
5,
Right.
5,
And nickel,
10.
right? And the C3PH3, cyclopropanol, because it is coordinated to three carbon centers. That's why the middle ring over there. So it will give you the 3 electrons. So 5 plus 3 plus 10, it's 18 electron species, right? So anyhow, I've told you the answer, but as you have participated, so you can just go through that once and attempt the assignment where it is being given, and this is the way you have to calculate your number of electrons given by your particular ligands and the metal center. And there you can just get to know how the electrons are coming into picture. Okay, excuse me a second.
Yes, ma'am.
All right. So now moving ahead, we have fifth question where it is asked, this is a reaction which needs some bit understanding, where it has been asked that you have a palladium Cl4 which is having uh, 2 sodium outside, so it becomes palladium Cl4 2 minus. So palladium here, if I tell you to calculate the oxidation state of this palladium, what it would be? So if we'll take the oxidation state of palladium as X, Cl will give you the -1 charge because they are 4 in number, and outside it is -2. If you calculate, X minus 4 equals to -2 and X equals to +2. So here your palladium is in +2 oxidation state, and when it is reacting with this allyl halide, this is nothing but this. This is allyl halide. So this is one of the reaction of allyl halide to form a species where your complex is having an allyl group. This is the preparatory method which you will get in your lectures. So in presence of carbon monoxide, which is acting as a catalytic amount they have been adding, and the other solvents, water and methanol, what could be the possible product for this thing that you have to undergo, where you need to see कि this is a reaction where allyl gets into your gets connected or coordinated with your palladium. So the two options would already been ignored, where this B1 and C1, because this is a straightforward reaction where your preparatory methods are coming into picture, metal allyl complexes. So B and the C options are gone. Now you are only left with the A and D option. Now you have to calculate and to draw the mechanism, how it is acting, how the loss and what carbon monoxide is taking into place. I will just give you that one hint that carbon monoxide is actually acting as a reducing agent over here, which will provide the electrons to your C3H5. Right now it is cationing C3H positive plus Cl minus. So this reducing agent will reduce it. That means it will give you the electrons, and then it can coordinate with your palladium. Right, palladium is already in +2 state, and this is being as an ionic form, it can coordinate with your palladium, and it will give you a certain complex which is having your metal and allyl direct coordination. So now you need to know and find it out whether it is A option or D option. So the only take home message over here is carbon monoxide, which has been acting as a catalytic amount. Why catalytic? Because it would be regenerating in the system. That's why catalyst is nothing but a species which would regenerate, and it is not taking part in the particular reaction. Understand? So that's why it is being taken as a catalytic amount, and it is acting as a reducing agent. So what is the role of reducing agent? It will give electrons to something. So where it is going, it is giving to the allyl, and how allyl then after getting reduced, it is attacking on your metal. That is the whole story, and you need to find out by following the mechanism. Now the moving ahead, the sixth question that we have is here. Here we have this question where don't get worried about by looking at the complex structure. It is nothing but a molybdenum complex where it is coordinated with a carbonyl group, two carbonyl groups, and one olefin, which is a diene, and this aromatic ring over here, which is having a CP bound and a positive charge. So here, if it is nothing but your nucleophile. So it has been, the approach is over here that alkenes, if we'll talk about generally, if I'll take this case, so these are bit inert. If I have to react a nucleophile, because already it is having an electron density. But when they get bind to a metal center, which is already having a complex with a charge, with a positive charge, so it polarizes this alkene bonds and the nucleophilic attack becomes very feasible. So very first question comes into picture, like where this R negative is going to attack, right? So this is positive, this is negative. The product is not having any charge. That means it is getting neutralized. So this could only be neutralized when R negative is coming into picture. Now where it will attack? The only position where molybdenum is connecting with this olefin, and this olefin becomes reactive, and one side it can attack. So here molybdenum, if it is coordinating like this way, the R will come, it will attack this side, this bond will go here, and this will come here. That's why, or we can say ki now these three carbons are now coordinating with molybdenum. Now it has changed from its eta 4 to eta 3. Why eta 4 to eta 3? Because here in eta 4, all the four carbons were involved. This A, B, C, and D. But as soon as the R group has attached, so the double bond has changed to the single bond. Now it is having H and H. 1, 2, 3, 4. Only the charge remains in this C1, A, B, and C. So that's why it has gone from eta 1 to eta 3. So when this has been added, so what you will call it as? So that what is being asked, whether it is an electrophilic addition. Since what is an electrophile, which should be an electron deficient. So R negative is electron deficient or electron rich. Hello.
Yes, ma'am.
So R negative is electron rich or electron deficient. Is it having
Electron rich.
electron? Right. So this negative sign itself says that it is electronically rich and it will attack. So the first option and the third option itself goes on, but they are not even considered because this is electrophilic addition and substitution they're talking about. So the first, this is the way you can eliminate your two options and then your focus would be on other two options. So since this R negative, which is coming into your reaction scheme, it is electronically rich, so it can't be an electrophile. This is a nucleophile. So either it could be a nucleophilic addition or it could be a nucleophilic substitution. Now you need to see whether it is substituting some ligand which is already negatively charged or it is getting added to that. Can you answer this, Chandan? Substitution, I told
Ma'am,
you, if I have a halide, if I have some X negative, okay, if I have some X negative, where metal ke saath it is coordinated, and if I'm giving R, so if it is attacking on this metal and X is coming out, what we call it? This is basically substitution. Substitution is nothing but you are replacing one thing with the other. You are substituting one thing with the other. So that is called substitution. But if substitution is not happening and it is getting added to it somewhere at one center, because if C eta 4 is there, it is still intact with your metal center and R group is just added over here. So it can't be substituted. It has not substituted or replaced a particular whole ligand. It has just added on to one carbon. So the answer becomes nucleophilic addition. Is that understood?
yes, ma'am.
Do you want me to repeat or more examples or something? Or is this fine?
No, ma'am, I just remember substitution reaction.
Okay. So now it is clear that firstly you have to see the reactant. What is your substrate complex? Only from there itself you will get to know how to eliminate the two options. Now again, the meeting will be end up in 10 minutes. So you have to join the same link again. Sorry for the inconvenience. Okay, so this is where we have come across key how we can eliminate two options and how we can judge whether it is addition or a substitution reaction. This is a bit part of organic, but how it is getting substituted also the mechanism is very important. It is changing its hapticity from eta 4 to eta 3. Hapticity is nothing but the involvement of your carbons. Out of the four carbons, if all the four are attached, that is where we have shown the sign over here. If out of the four, three are involved, that is hapticity 3. Now we are moving to the seventh question, which says that for the following products, C3H5MnCO whole 4 and C3H5MnCO whole 5, the C3H5 ligand is bound to metal respectively in what fashion? We have already seen कि allyl, this is C3H5. Firstly, we should identify what kind of ligand it is. This is the allyl ligand. And now allyl, we have already known कि this mainly exists in these forms, where it is in eta 1 positions and eta 3 position. Now you need to find out, these are the two complexes, how you will get to know that allyl is acting. Okay. Is it still on? Okay. So how it is acting, either this is an eta 1 or eta 3, or out of the three, two carbonyls are acting. For example, here, if two metal centers and the three are connected to something else, so it is eta 2. So out of these three forms, how it is coordinating with the metal center. So can you please try this particular thing, C3MnCO whole 4? What should be the hapticity of this allyl ligand? Hello, Chandan, you understood the
Ma'am,
question?
please. No, ma'am. That's why I was asking. Please repeat the
Okay, I'll
same.
just repeat it again. So what you have to do, I will just open this dashboard. So here they are asking, you have C3H5 MnCO whole 5. C3H5 MnCO whole 5. So you need to tell कि either it is in eta 1, eta 2 or eta 3 form. Firstly, you need to identify the C3H5 is your allyl ligand, right? So it could take this form also, where it is bound with the metal in eta 1 only coordination with the carbon 1. This is carbon 1, this is carbon 2, this is carbon 3. This is in coordination with that, so it becomes eta 1. If you have some other group over here and you have metal here, that means C1, C2, C3. Out of C1, C2, C3, which are coordinating with metal? Can you please answer? Hello? It is fine. Saying the wrong thing is also fine. You just need to give an approach to that so that I'll be able to know whether you are able to understand it or not. So metal is coordinating to how many carbon centers in this particular form?
What, ma'am?
Metal is, we were talking about ki here the metal is coordinating with carbon 1. That is called as eta 1. Now here metal is coordinating with how many carbon centers?
2.
Which one?
Ma'am, C2 and C3.
Right.
2 and
So this,
C3.
yeah. So this gives you eta 2. Hapticity becomes eta 2. Now if I have a third example where C1, C2, C3, all three are coordinating with your metal, then it will be a hapticity 3. So this allyl, one single allyl ligand can coordinate with a metal center in three different fashions, eta 1, eta 2, or eta 3. Now the question is that this is the complex which is being given, and you need to find out in what fashion it is actually connecting with your Mn. So in place of this metal, they are giving you metal center Mn. So now you need to find out whether Mn is coordinating with C3H5 in eta 1, eta 2, or eta 3. So that is the question. So how you will get to know in which form it is coordinating. So I will just tell you in brief. So we know that 18 electron complex is the stable complex, most stable one, right? We know that. So when we have this C3H5 Mn CO whole 5, we will calculate its total electron count. If I'll say ki I don't know the hapticity of this particular C3H5, and I will take it as X. Now Mn will give how many electrons? Manganese is, the atomic number of manganese is 25. And how many electrons it will give? Hello, Chandan, can you answer?
Yes, ma'am.
How many electrons will manganese give? So it will give you 7 electrons because it is having D5S2. When you total calculate it, it comes as the T7. It comes in this particular form.
3D2 and sorry
3D5,
3D5
4S2.
and 4S2.
Huh.
Yes, ma'am.
That is its free form, but right now it is in complexation. So we take the whole 7 electrons. So it will give the 7 electrons, right? Now carbonyl is a neutral moiety which gives you 2 electrons. So 2 electrons, since they are 5 in number. So total they have to form an 18 electron. The stable complex they will form, and that would be having a total electron count of 18. So if we'll cross calculate it, X plus 7, this becomes 2 into 5, that is 10 electrons. This is also electron. This is 18. X plus 17 is equals to 18. X equals to 1. Now, if we got that contribution of C3H5 is 1, which means its hapticity is 1. So it is coordinating only via one carbon. It is understood?
Ma'am. Ma'am.
Okay. So similarly, there is one more complex in the same thing. You need to calculate. We have done for this C3H5 MnCO whole 5. You need to find out ki what is the fashion, in what fashion this C3H5 is coordinating when there is one less CO. Can you try this? In the similar way, you have to calculate.
Yes, ma'am. I can try.
You please try. I think less than 1 minute is left, so you just rejoin the link, okay?
Yes, ma'am. Yes, ma'am.
Mansi, you also rejoin the link because this meeting will be ended.
यार पहले वाला ही हमने अच्छा था तो अच्छा लग रहा है मैंने खोला ही नहीं